Hello and welcome, Nord Anglia, and thank you for joining us today for our MIT Abstract with MIT graduate student Nemo Hsiao. I'm your host, Fatima Hussein, and I'm a PhD student at MIT studying ancient Earth. Now, before we begin, I'd like to cue our listeners into what an abstract actually is. An abstract is just a snapshot or a summary of a greater work of research or writing, and with this series, we're bringing abstracts of inspiring MIT experts straight to you wherever you are around the world. I know we have a lot of classrooms tuning in today, so welcome all. Now I'd like to introduce you to Nemo, who's going to tell us all about his cool work in soft and micro robotics. Welcome, Nemo.
Hello, this is Nemo from MIT. So today I'm going to introduce you to some of the robots that fly like an insect. So let's say imagine you're inside a factory and there are so many pipelines like going around, and some of them might contain toxic gases or liquid. And if there's a problem, then you probably don't want human being to go near to those toxic gases. And that's a point that you would like to send some of the tiny robots to go into those pipelines to see what happened. So right now I'm going to show you a picture of how this tiny flying robot look like. So this is a picture of our robot. The one in the yellow circle, yellow square, that is me. That is not a robot yet. The one in the orange square is the microscope. So that's the point that you ask, okay, where's the robot? So the robot is actually right under the microscope. And it is so tiny compared to a human being that I need to give you a German version. So this is how a robot look like in our lab. And yes, that is the thing, that is my finger. So if you put this type of robot beside a bumblebee, this is how it's going to look like. And you can see they have the wing that is around the same size, and they have this body that is around the same size as well. So what I'm going to do today is I'm going to introduce you to a series of tiny flying robots that are developed by researchers from Harvard University and here at MIT. So the first question that you can ask is, how are this tiny flying robot different from traditional flying machine? So listen up, this is something that you can go home and teach your parents. So when you're talking about flying machine, the first thing that comes to our mind is the airplane, right? The traditional airplane, they have wing so that they can fly. But when the airplane is flying, you don't see airplane's wings going up and down like this. That would be really scary. So they are usually they stay there all the time. So we call them fixed wing airplane. How about some of the commercial drones that we see nowadays? They use spinning propeller. So when they fly, they spin their propeller. And if you take a look at the robot that I just showed you, they don't have a propeller. They do have wing, but their wing is not fixed. So when they are flying, they actually flap their wing, just like tiny insect. So we call them flapping wings. So this robot actually, they all have flapping wings. And this is exactly how it works. So you can see on the right-hand side is a robot that we developed in our lab that it flaps its wing. On the left-hand side is a bumblebee that is flying. So you can see the wing motion is kind of similar. So today I'm going to teach you how to make those wings and how to investigate, how to take a look into those flapping motions. So the way we do it is we try to make a wing first. So here's a wing under the microscope. And next step will be putting the wing onto the robot. That's my finger holding a tweezer and try to put the wing onto a robot. And then we try to flap it. This is what you're gonna see when you flap the robot. Oh, you can see, oh, there's something moving And after a while, it stopped moving and then something moving again. You cannot see very well. That is because the robot is flapping so fast that it's so hard for our human eyes to see it. So since we cannot see it, we let something else to see it for us. So in our lab, we have a very special camera that will be able to slow down the entire motion. It will be able to capture video and slow it down by a lot. So what we're gonna do is we put our special camera there and we put our robot there. And then that's a point that you press the button and say, hey, flap, and hey, trigger. And after that, this is a video that you're gonna get, a beautiful flapping motion. And this video is actually 1,000 times slower than what it actually happened. So the question you're gonna ask is, okay, so I know we have a really slow video showing the flapping motion, but how fast does it exactly flap? So here I'm gonna tell you, a human being like me, I can probably do like 3 flaps in a single second. That's what you're seeing on the screen is my hand. So I can probably do 3 flaps. And you can probably do slightly better than me, but probably not more than 5 flaps. But our robot in our lab can do 400 flaps in a single second. That's the reason why we need 1,000 times slower video to see what is going on and to change some of the parameters of our mechanism to improve the performance of the robot. So once we have this flapping motion, we'll be able to fly and we'll be able to stay in the air. But even more than that, I'm going to introduce you to Robot 2. It doesn't only fly in the air, it can actually dive into the water and swim inside the water and then pop out from the water and land on the ground again. So here's a series of videos showing you how this robot works. So on the lab, you can see the robot flying when it's flapping its wing. And in the middle, you can see the robot swimming or like popping out from the water and also landing back to the ground. So this is how capable of this number 2 robot is. But it has a major drawback, like there's something wrong there. If you try to poke the robot a little bit, then it will break instantly. So it's actually really fragile. So what we think of is, if we try to poke our human muscle, it doesn't break. So instead of having some other actuators, we try to use an artificial muscle that mimic a human muscle so that when we are in collision, the robot doesn't break that much. And so one thing so cool about this robot is that you can put it into 1, or you can connect them with 2, or you can have 4 robots flying together. So here's a video showing 2 units flying together. So you can see it's like spinning around, but it's still flying. And most importantly, you can see 4 robots flying. And if we try to hit the robot, it will go to the ground, but it will be able to recover and get back to the air. If we can see that again, it goes to the ground and come back again. Even more impressively, the robot can do a somersault. It happens so quickly, so I have to play it again with the slower motion. So this one shows you the robot take off and try to hover a little bit. And after a while, it try to ascend. And after it gets to that point, it actually flip over and bounce back. Okay, eventually it will recover. And this is a point that we think of, we can do a lot of crazy maneuver, but can we do something a little bit different? And that's a point that I would start to look at Firefly. So the Firefly is something that it will emit light during at night. And here on the right-hand side, we show that our robot can actually emit light if we try to trigger it if we try to send some signal to the robot. So on the upper right corner, you see there's no color coming out from the robot. On the lower right corner, you do see there's some color coming out, and we can even put some pattern on top of that. And here's some videos showing you how this Firefly robots operate during the night. So you can see a lot of tiny light coming out from the robot. Okay, so you see a lot of like cool, successful video. But what actually happened in the lab are a lot of failures. So things go wrong a lot of time. Like what you see on the left-hand side, the wing actually flew off from the robot. And so you can see the wing slightly going off the frame. And on the right-hand side, the robot simply just crashed after flying for a while. So this is actually really normal during a research cycle. So inside the research cycle, what you're gonna do is you're gonna get a piece of paper and a pen, try to work out the math. Like what I'm showing here is like so complicated right here. But if you actually work it out, then that's a point that you can try to build a robot. After a couple of days building the robot, you will get a nice looking robot like this. And then that's a point that you try to test it. And most likely it's gonna fail. But this is the most important part. Failure is so frequent that happens in our entire research cycle. So we see that like all the time. But the most important thing is after you fail, you need to think about why you failed and then come up with a different solution, come up with a different plan, and go back to the very first step and redesign the robot. And then that's the point that, oh, you build it again, you have another new robot, and then you go test it again. And after a couple of cycles, that's the point that you will be able to get some of the videos that is really cool that I just showed you. Okay, so what you have learned today and what you're gonna go home and teach your parent is you have seen a series of tiny flying robots, and they have flapping wings. And most importantly, how fast do they flap? They flap for 400 times in a single second. So these two are the takeaway, and these two are the things that you're gonna go home and teach your parents, because I believe they definitely don't know about this. So in the end, if any of these flying robots are interesting to you and you feel like, hey, I want to make this robot by myself in the future, if you feel that, do study physics, do pay attention to math, and one day maybe when you're in college, you can choose to major in science or engineering, and that's the point that you will be able to join us and make one of these robots yourself. And thank you so much.
Thank you so much, Nemo. That was totally amazing. So I have a quick question to kick us off while the students input their questions to the Q&A right now. What do you do when you're not building these robots?
Oh, that's actually a really good question. So when I'm building this tiny robot, I'm usually work under the microscope with my hand, moving just a bit. But when I'm not doing that, I play baseball, which is kind of like the opposite. Like, oh, I'm holding like a heavy bat in this hour, and next hour I'm like going back and try to do all this tiny robot. So this is kind of cool for me to like switch back and forth. But that's what I'm doing when I'm not making the robot.
Okay, let's dive into this Q&A now. Oh, wow. Now that I have you on full screen, Nemo, I have to ask, where are you? What are we looking at?
Oh, I'm actually right inside my lab. So if you can see, those are some of the equipment that we have in our lab. The specialized camera right there, that is the one that I just showed you in the picture that will give you 1,000 times slower videos when we try to look at the flapping motions.
Wow. Okay, that is really, really cool. Okay, we have a fantastic question from a Nord Anglia student named Smayan. And Smayan is asking, what is the power source for your robots? Where do they get power?
Oh, Smile, that's a really, really good question. You should probably join us at some point. So the power cell, right now, unfortunately, we don't have battery on board. So we have those tiny wire coming out of the robot, and that will plug into some of the plug. You just like plug into the wall, and that's how we power it. So unfortunately, we don't have battery on board at the moment. But that's a really good question, and that's something that we try to work on.
And that actually leads into another question from a Nord Anglia student who's wondering, eventually, will you have these robots without those wires attached using batteries, or how would they handle it considering that batteries are so heavy?
Yeah, this is a great question, and this is something that actually one of my colleagues is trying to work on. So recently he tried to get some kind of battery and some circuit on board, like we put it on top of the robot and we try to fly it. And of course it didn't work as usual. It didn't work, but he is still working on it. And at some point we hope we'll be able to do that.
Got it. And we have another Nord Anglia student who's wondering, so you're building these robots at a microscope. What are the tools you're using? Are you using tweezers? What does it look like?
Yeah. I'm just gonna show you. Give me a second.
Sure.
Yeah. So we use this kind of tiny tweezer in our lab.
Oh,
So
wow.
when we are moving, we don't move like our hand like this. We try to move our hand like tiny bit just to adjust like the angle, how we install the wing, everything. So we use like tiny tweezer. And you're
Wow.
yeah.
Okay, and that leads me into another question that's in line with building these robots. What are those wings, those flapping wings, actually made out of?
They made of like mainly two materials. So first one, there's some like wing structure. We call it like spar. Those are made of by like carbon fiber sheet. So that's actually very similar to what you have inside the pencil. So that's the same material. And the other one, the airfoil, is made of plastic, specialized plastic. It's very similar to what you have in of like a plastic bag from a supermarket. So plastic bag and something that you have inside the pencil. Yeah, it's actually not that complicated.
Got it. Okay, and then we have a question from Oliver, and Oliver's asking, what's the artificial muscle made out of then?
Oh, great question, Oliver. That's really tricky. That's we make like the best those like artificial muscle. So we have multiple layered of elastomer. So you can imagine elastomer as some jelly, like jelly that you eat. So when you squeeze the jelly, it doesn't break all the time, right? You will be able to like expand itself a little bit, deform a little bit, but that made of something like a jelly.
Got it. And now we have another question from a student who's wondering, did you always make teeny tiny robots? Is it possible to make robots the size of birds? What other robots can you make, Nemo?
Okay, so in our lab, we try to focus on tiny robot because that is already overwhelming. It's really hard to make. And it has the advantage of like going into some very tiny space, like a pipeline or like a dock, and you can go inside with the tiny size. There are some other brilliant researcher out there at Stanford University, and some of them at MIT as well. They try to make larger robot, and they actually make robot that fly like a bird as well. But then that's a point that you won't be operating them inside a factory, inside the pipeline. But some of them are working on that, and they are doing a great job as well.
Got it. And right now, the top question we have in the Q&A, Nemo, is from a student who's wondering, will we ever be able to make something similar to the flying robots with the things we have at home?
That will be a little bit challenging. Like, so we have actually, you can see behind me, we have like so many equipment. We need to have like microscope. We have a lot of sophisticated equipment in our lab. So that will be a little bit hard to make something that actually works at home. but you are definitely welcome to try to make some of the model that you can simply just put it on your shelf. And that will also look super cool as well.
Got it. And they can also build maybe bigger things in the meantime also.
Yeah, of course, of course.
Okay, we have a question from Bethan. And Bethan's wondering, how many failures did you have to go through before you managed to get one of your first successful flights?
Great question, Bethan. So sometimes I will need to like try to build a robot, and that might take me a couple weeks. And then we try to tune the robot. We try to fly for a couple times, and then that will be like a month or two. And sometimes like after 2 months, 1 month or 2 months, and I got like one successful flight that I can show you, just like the video that I just showed you. So it's sometimes like I'm like struggling a little bit, try to get things right, but like after you get things right, it's actually really rewarding.
Awesome. No, that totally makes sense. So now we have a question from a student who's wondering, how does that artificial muscle you described earlier actually work? Does it act the same way as a human muscle, or is it different?
Of course, it's a little bit different from the human muscle. So the way we think about it is we try to mimic the motion. But then that's actually, so I was talking about those like jelly thing. So we try to expand that jelly a little bit, or like squeeze the jelly a little bit. That's how we create the motion. And that is somehow a little bit similar to what human muscle does. So human muscle, you can also like expand and squeeze in one direction. So we try to do it in one direction. So I would say that's kind of like, it's not exactly the same, but like extremely similar.
Got it. And we have a question now and it's asking, how does a robot's wings know to flap? Do you have to put computer code into it? How does it know what to do?
Oh, that's a great question. So you can see those. I think I can show you. You can see those tiny instruments there.
Yeah.
They are actually one type of computer. So when the robot is flapping, the computer is computing how you should flap. So let's say if my robot is like going this way, then what you're gonna do is like, oh, you try to flap this wing a little bit harder. So that's computer try to compute. And then once you flap it harder, you will recover to the nominal state. So that's how you balance yourself. And if you go on the other side, then you try to flap your right wing harder, and then you can come back.
Got it. Okay, so there's a lot of computer work behind the scenes to make these robots fly the way they do. And now we have a very fun question from a Nord Anglia student, Nemo. So get ready. Did you like bugs before you started making robot bugs? Did you already like bees?
I didn't like it that much when I was a kid, but it's like after seeing so many cool flying robots, I was like, I want to do something smaller. I want to do smaller flying robot. And that's a point that I feel like, we need to look into the nature and see how those insects do their job, because they are doing an amazing job of flying. And we can learn from them to design those robots. And this is actually what we're doing in the lab. Is like really successful story that we actually mimic. We try to learn from the insect and try to build our own robot. So I didn't like insect at first, but now I start to like liking it.
Okay, I think I've started to like it too, just based off of your presentation alone, Nemo. That's way too cool. And now we have a question from Abhiraj, and Abhiraj is wondering, what are your next steps for these flying robots? How do you think you can make them even better? He says they're already cool, but he wants to know what your future plans are to make it even cooler.
Okay, great question, Abhiraj. So this is what we are talking about with like a lot of professors nowadays. So you should be the one who joined us in the future as well. First thing, of course, is what some other student mentioned before, the power. So right now we are flying with a power that plug into the wall. We want to get rid of that. We want to put battery on board. And right now, like this kind of flying robot can only fly for like 10 seconds 20-second maximum. We would like to love to have them fly even longer. So that's like the two primary goal for now.
Got it. And now we have a student who's wondering, how did you actually get into making robots in the first place? What led you to this?
I started to make robot when I was an undergrad because I feel so excited seeing those drones flying in the air. So that's a point. When I was an undergrad, I made a drone by myself, like during the class, and I was like, that is so cool. But I want to make something even cooler. So like switch to an even smaller version. That's what I'm doing in the lab nowadays.
Wow. So for the students on the call who might not know what a drone is it correct to say that a drone is like a flying robot that usually has a camera on it?
Yes, exactly.
Okay. And then we have a follow-up question from a Nord Anglia student then. Do you think you will ever put cameras on these tiny robots?
It will be challenging because like camera has some weight and we have very limited payload for those camera at the moment. But hopefully we will be able to put some other sensor on the flapping wing robot, on the tiny flying robot, and it will be used in some search and rescue mission.
Got it. And speaking of those missions, could you walk us through one more time what scenarios these robots might be used in? How would you use them in a factory, for example?
Okay, so let's say you have so many pipelines in a factory, and there's probably one leakage, but like those gas inside those pipeline might be toxic. So you don't want human being to go around that because that's just bad for like human beings. So we want our robot to fly inside those pipeline. But if the size of your robot is too big, then you won't be able to get inside the pipeline. So we want like very tiny robot. So the tiny robot will be able to like navigate or like just flying inside the pipeline so that you will be able to see, oh, where the leakage is. And that's a point that you say, maybe I can fix it here. Maybe I can send some other material here. Yeah.
Got it. Okay. So there's two things in that answer that I'm sensing. So basically, these robots go where it's too dangerous for humans to go. And then also it goes places that humans can't reach because we're too big. Is that about right?
That's exactly right.
Cool. Got it. We have a question now from a third grader Nord Anglia student, and it goes like this. Hi, I'm in the third grade. How can I start to make robots like yours? What materials do we need? So what should this third grader do to get started making robots in general?
I will say the material that we use in our lab are more or less like very specialized. So you probably won't be able to get exactly the same material through Amazon, but you can get something that is slightly larger and maybe slightly cheaper, like a Lego or anything that like a motor that move around. And that will give you a sufficiently cool robot, and you will be able to make that in your home.
Got it. Okay. I definitely am going to look at Lego robots by myself after this too. So maybe the student and I can look together. Okay. We have another question from Nord Anglia students wondering, we have a couple people asking this actually. What sort of light do you use for those glowing light robots, the Firefly-like robots? What kind of light is that?
So that is actually embedded. That is actually inside the artificial muscle. So we put some very special particle that and then we put that inject them into that artificial muscle. So when the muscle is moving, that's a point that they emit light. And you can choose by changing different type of particle, you can change different type of light. So you probably have seen that they're like yellow and blue or like green light. So you can try to tune the recipe a little bit, and then you will be able to emit different colors of light.
Got it. And now a student is wondering, if you didn't have the wires attached to the robot, would it fly at all? If so, how long could it fly?
So right at this point, everything is coming out from the wire, unfortunately. But that's something that we try to work on. So if you just like unplug those wire, it won't be able to fly at all. And you're absolutely correct. You're like
Got it. And so here's another fun question for you about how you're building the robots. So of course you showed us these very cool tweezers that you use. You told us about the very fine movements you have to employ. Are you building these robots yourself from start to finish, or do you build certain parts and your lab mates build certain parts? How does it actually work in your lab?
Oh, that's a really good question. That's a really good question. So what we're doing in our lab is one of my lab mates, Suhan, he's making those artificial muscle. So what happened is he made those components, like tiny components separately. So then he handed to me in a tray. So like in a tray that probably like in a tray like this. There are like so many components around, and that's a point that I need to use tweezer to pick them up and put them together. So he's the one who make the component. I'm the one who assemble the robot. So it's actually like a production line. And then that shows how important collaboration is. So you really need to collaborate with each other, because I'm really good at assembling and he's really good at making components. And for a robot to fly, it's really important for like both of us to make good part together.
Got it. So there's a lot of teamwork involved.
Yeah, definitely. You definitely need to rely on each other's, and then you definitely need to have a lot of communications and try to like work with each other.
Got it. And now we have a question about the ideas and inspiration behind these robots. Okay, so we have a student, a non-English student, who asks, did you get the idea to make these robots from a dream, or where did it come from?
It's mostly I don't think we get it from the dream, but like we do get it from like looking birds or like insect flying in the air. So it's more like sometimes we say, we want to build a tiny robot. And how do we do that? And then we walk around on like MIT campus and we see like butterfly flying, we see bee flying around. And that's a point like we're like, so bee can do so like they can fly so well. So maybe we can do something that is similar to that. And that's where we get those like inspiration.
Got it. So you have to go around and be observant of nature and see if there's things that we can recreate in the lab.
Yeah, of course. Yeah.
Got it. We have a North English student who wonders, do you also build robots for fun when you're not in the lab?
Some of them. I build like robot that help my life a little bit.
Tell us more.
So there's a mechanism that I can like charge my phone wirelessly, like in my room. That's like a really simple one. But so what happened is like, if I just like place my phone on the table, then the phone will somehow automatically attach to the wireless charging pad. So yeah, definitely try to make something by yourself. Most likely you're gonna fail in the first or second round, but it's okay. And try to figure out what goes wrong during the process, and that's a point that you will succeed in the end.
Got it. That actually leads really well into something that a few North English students have been asking. When you are taking those very, very cool videos of the robots and you see something has gone wrong, how do you trace the problem? Do you take the robot back under the microscope and look at it? How do you figure out what's the source of those failures and how do you solve them?
That's a really good question. That's actually the most challenging part. So when we take those videos, those are like really slow motion, and then it always goes wrong, like in 0.001 second. It's like very, very quick. It happened like very, very quick. So you need to go into those video, play them frame by frame. So you say, it's still okay at this point, and then all of a sudden it goes wrong. And what happened in between? You need to look at them first. And sometimes it might be obvious, sometimes it might not be. when it's not obvious in the video, that's a point that you take the entire robot under the microscope and take a look at them. So they're absolutely right. We need to look at them under the microscope.
Got it. We have a student who I think is very curious about your journey into making robots. And you mentioned you started during undergrad, but we have a student who knows, what's the first robot that you ever saw?
What's the first robot I ever saw? I will say there was a 3D printer in my high school when I was a high school student. So what happened during that class was like, we can try to draw something in the computer. We can draw a 3D model in the computer, and the teacher let us 3D print it. So that's kind of like the first robot that I saw. Like, because like 3D printer is actually kind of a robot, and you can see the printing process, and the nozzle is moving around. So I would say that's kind of like the first robot that I saw back then. But that was roughly 10 years ago from now. Nowadays, like you see a lot of robots like flying around, like commercial drones with camera on board that give you like aerial footage, and also a lot of like robots inside the factory that you probably have seen on the news.
Got it. And we have a question now from David. And David is wondering, what types of payloads can these small robots actually carry right now? Can they carry anything at all?
So it's actually really limited, David. So the entire robot is actually lighter than a single coin, like a single penny. The entire robot is lighter than that. So the payload is roughly slightly more than the robot itself. So it won't be able to carry a single penny at the moment. But we are trying to work on that. And the goal is to carry a penny within like half a year or like a year.
Wow. Oh, that is very, very cool. And now we have a question from Kush. And Kush is wondering, eventually, do you sell these robots to the factory so that they can figure out their problems? What will happen to these robots in the future?
Great question, Kush. That's definitely something that we talk with MIT professor every day as well. One of the biggest challenges that we face is reliability. So right now, it might fly when we build one, and it might not fly when we build another one. So reliability is actually a big problem. If we solve that, we'll be able to sell them to other company, or even like send them into factory, so that they can actually help people to investigate to see what goes wrong inside the factory.
I see. And we have students who are very intrigued by the power source for these robots. And I think some of them, maybe they've already started taking physics or learning electricity, perhaps, because they want to know how much energy does your robot use and how long can it fly attached to those wires?
So they actually consume very little energy. So it's just slightly more than some of the LED light bulb, slightly more than that. Yeah, so this is actually not that much, but the problem that prevented from like flying longer is a lot of mechanical component breaks. So as you can probably see me in the previous video, a lot of wings flew out. That's what prevented from like flying for a longer period.
I see. Okay. So then following up to that, we have a student who wonders, they think they counted about 4 wires attached to each robot. They want to know, if you remove one of those wires, does the robot still fly?
So what happened is those 4 units actually try to balance each other. So if you remove one wire, that unit won't be working. So the entire robot gonna crash in that way, because that robot is not providing any lift force to come out. So the entire robot is gonna crash that way. But that leads to a really interesting research topic that we are working on, is that if we connect more and more tiny robots together, So even if one fail, if we just cut one, then the entire robot should be flying as well. So that's a really good question, and that's something that we are working on right now.
Got it. Okay, so Nemo, we have seriously at least 50 questions left in the chat, but we don't have as much time to answer them. So I'm going to leave you with ask you with one question. What would you tell these students who want to build robots in the future? Let's say they want to do a PhD in robotics just like you. What advice would you give them going forward?
I would say be curious about everything. So when you see something that works, for example, let's say, oh, if you see an elevator that works, that's moving around, or you see any type of mechanism that works in your life, or anything, any robotic stuff in your life, don't just look at them. Think about, why does it work? How does it work? And if you don't know the answer, you can just Google them. And there will be a lot of people explaining how it works on YouTube. So do be curious about everything, and be curious about what's the working principle behind that. And of course, try to focus on math, try to do physics, try to spend your time studying those subjects. And then eventually you might be able to choose an engineering or science major, and then you will be able to make one of the robots that we are doing nowadays in our lab.
Awesome. Okay, Nemo, that is very, very good advice. So to the students on the call, take Nemo's advice if you want to build robots. And if you want to rewatch any part of today's abstract with Nemo, you can find the recording on YouTube and Global Campus very soon. And before I let you go, I wanted to let everyone know about a couple more abstracts we have coming up that are going to be super cool. Later this month, in November and in December, you can learn about brains and solar panels and perhaps even jump rope. So we have some very, very exciting things coming your way soon with MIT abstracts. But for now, I wanted to thank you all for joining us today. And I wanted to thank the MIT Nord Anglia Education Collaboration for making this series possible. And most of all, thank you, Nemo, for sharing your expertise and time with us today. This was super, super cool.
Thank you.
Awesome. Okay, goodbye, everyone. See you next time.